Welcome to the world of mechanical engineering. To understand how machines move, we start with Newton's three laws of motion. These laws are the foundation for every car, robot, and engine. Imagine designing a robotic arm. You need to know how much force is required to lift a part, how fast it can move, and how it affects its base. Newton's laws give us the tools to answer these questions. They connect force, mass, and acceleration, turning guesswork into science. Without them, engineering would be unpredictable. These principles are essential for building safe, efficient machines. From elevators that accelerate smoothly to cars that brake safely, Newton's laws are at work. They're not just textbook ideas, they solve real-world problems every day. Every moving system starts with these laws. They are the key to safety, efficiency, and innovation in engineering. As we explore these laws, think of them as your guide to understanding every machine around you. Mastering them is the first step to becoming a great mechanical engineer. Newton's first law, the law of inertia, says objects at rest stay at rest, and objects in motion stay in motion unless acted on by an outside force. A flywheel in an engine is a perfect example. Its inertia keeps it spinning smoothly, storing and releasing energy. Or think of a conveyor belt. When it stops, the boxes keep moving for a while due to inertia. That's why stopping a train takes so much force compared to a car. Ignoring inertia can lead to unsafe or inefficient systems. Now, Newton's second law, how force creates motion. This law tells us that acceleration depends on the net force applied and the object's mass. The famous equation, F=mxa. This lets engineers calculate exactly how much force is needed to move something. For example, to lift a 10 kilo part with a robotic arm at 2 metres 2, you need 20 newtons of force, plus enough to overcome gravity. This calculation is the first step in choosing the right motor or actuator. The second law also works in reverse measure acceleration, and you can find the force causing it. Engineers use this to diagnose problems, like using accelerometers to measure vibrations and calculate forces inside machines. Without this law, designing or troubleshooting machines would be guesswork. It's essential for everything from sizing motors to ensuring safety. The second law is a powerful tool for both design and analysis. It connects the dots between force, mass, and acceleration. Every mechanical system relies on this relationship. Finally, Newton's third law. Every action has an equal and opposite reaction. Whenever one object pushes another, the second pushes back just as hard. This is why you feel resistance when you push on a wall. In machines, this law is everywhere. Gears are a great example. When one gear tooth pushes another, the second pushes back equally. Engineers must design parts to handle both action and reaction forces. In engines, when gas pushes a piston down, the piston pushes back on the gas. Every part in a machine experiences these force pairs. Even simple bearings. The shaft pushes down, the bearing pushes up. If the bearing can't handle the reaction force, the machine fails. The third law reminds us that forces always come in pairs. You can't analyze one part without considering its effect on others. It's a law of balance and interaction. Understanding this is key to building reliable machines. Newton's three laws work together in every machine. Take a car. At a red light, it stays still. First law. When the driver accelerates, the engine creates a force. Second law. The wheels push back on the road and the road pushes the car forward. Third law. The car's inertia resists motion until the net force overcomes it. As the car moves, the net force, engine minus friction, determines acceleration. The heavier the car, the more force needed for the same acceleration. Engineers use these laws to design engines, brakes, and every moving part. When forces balance, the car moves at constant speed. First law again. When unbalanced, it speeds up or slows down. Second law. Every force, from tires to pistons, comes in action-reaction pairs. Third law. Understanding how these laws interact is the key to designing efficient, safe machines. They're not just rules. They're the language of motion in engineering.